Hey, it's me, Steve. There's the date. And I haven't done one of these in a while, but I'm going to go through a math problem with you guys. Basically, this is a real world scenario with real numbers. Someone asked me to figure this out for her, and I did. And then I got, trying to see if I could derive an equation from it and all that stuff. But first, we're going to handle it as simply as we can. Here was a question about how many of my 5-person staff miss work per day out of a typical work year. All right, the typical work year in this case has 250 days per person. Between all 5 people, they get 175 days off in a typical work year. All right, there are 2 ways we can handle this problem. All right, we can either use all 5 people, or we can reduce the problem down to 1 per person. All right, we're going to get the same number in this case, but I'm going to derive the equation from here, and I'll explain why for a second. So we basically take our 250 days per person, we multiply it by our number of people, and we get the total amount of days those people work. All right, then the second part of our equation is they all collectively have that 175 days off. So we divide it by the total number of days worked between the 5 people, which is 1250, which you got here, and we get 0.14. All right. Now we can reduce the problem and do it, as per 1 person without using all 5. And simply how we do that is we take the 175 days off, divide it by 5, and we get 35. All right. That's just a number. All right. That 35 would be about how many days off each of those 5 people has if you evenly spread it. All right, so then we take that 35 and divide it by 250, which is how many days per person. And since this is a per person number, and this is a per person number, we divide and we get 0.14, but we're not done there. All right, we have to take this 0.14, which we got in each equation to be the exact same number, or each scenario, each way we worked it. See, there are multiple ways to work on one problem. And we multiply it by 100, and we get 14, which is equal to 14%. So that means in an average day, about 14% of the workforce is not present. But that doesn't give us how many people per day. In order to get that, we have to take that 0.14 and multiply it by the number of people, which gives us 0.7 people are absent per work day. Now, that's not a real practical number. I mean, if you're a numbers person, you understand what that means. But, people aren't in parts, at least most of us. So you get 0.7 people absent per day. That isn't practical. So there's a couple ways we could do this. I chose to get it to an even rounded number of people. In this case, 0.7 is close to, it was exactly 7/10. So I'm actually unsimplifying the problem, I guess, which equals 7 people absent per 10 work days. There's your 7 people, there's your work days. You also could have done this 0.7, you could have multiplied it by 7 instead of using 10, and you would have got 4.9 days per 7, you would have got 4.9 people absent per 7 days, which is close to 5. So you could round that and say 5, people are absent every 7 days. That would have been acceptable as well, but this is an exact number. You didn't have to round to get it. All right. So how do we express this mathematically? All right. So based on these 2 above here, I basically made variables. All right. And for all of these, this is what those numbers mean. So I set up these 2 equations just like I did here. This is 1 part, this is 2 parts, second part, first part, second part, all right? 1 and 2, part 1, part 2. And then I just plug the numbers in, all right? Now here, I did the same thing. Part 1, part 2, plugged in the numbers, I got 0.7. And my n, is that 7 people absent per 10 work days, all right? Now, I originally tried to see if I could simplify and combine these 2 linear equations and see if I could combine them into one equation. Now, when I used this one, it wasn't working. It works in this case. I derived it and got the exact same one as the one I'm going to show you here in a second. But it turns out that when you start plugging in other numbers, it doesn't work. It's a special case. Then I realized why. It's a special case because you're reducing it down to one person per. You're not using the total number of people in this equation. You're actually taking them out of the equation. You're reducing it to one person's absence. Okay, so that's why that didn't. It happened to work out in this one, but this example. But outside of that, it doesn't work. But you can do it with these. So now remember, these are the same as these up here. All right, so I just rewrote the problem here. These two, equation 1, equation 2, and we start to see if we can combine them. So this is equation 1, this is equation 2. Now, I want to get v by itself because v is over here. There's a number of ways I can do this, but I did it this way. So I divide by y, and since I divide by y here, I have to multiply by y here. And when I do that, they cancel out. So that's the second part of the equation. Okay, so my first part's still the same. Okay, equals v, but now I have v equals n times y. These are the same variables, all right? They cancel out, okay? So then they're all both on one side of the equation. So now I have my original equation, my original number 1, step 1, which still has not changed except the v is now gone. And I have taken this equation and moved it down here, all right? So they equal each other now, kind of, not really. We're getting there, almost there. But this is the same as this. All I did here is whenever you have something like this, you can always make it a fraction. You just divide by 1. There is a fraction there. It's always there. We just don't write it over here. Well, here we write it here, and the two y's cancel out. So we're left with z divided by x is equal to n over 1, and we can drop the 1. So it's the same as z divided by x is equal to 1. Well, how can we verify that? So this was our original two-step equation. This is our reduced equation, when we combine the two linear equations. So just so you look, I'm not going to go through these. You can check my math. But my x, y's, and z's, I gave different numbers for all of them. And then I first ran it through here, which would be this part. And then I ran it through this equation, which would be the simplified one right here. So this set is these two-part equations. This is this one-part equation, and that holds throughout the other cases, except in this one I started putting the this equation up here in case 3 and case 4. And as you can see, it all works out. But case 5, what I did is I increased all the numbers because I'm trying to keep this a realistic world scenario. So I couldn't go over 365 days, but I increased the number of people a lot and their hours of time off, and it still works. So this equation right here works for solving this type of problem. All right, that's it, and I hope you learned something.